Good morning. Today, I'd like to finish talking about this partial fraction business. Previously, we said we were going to look at integrals of the type integral p of x over q of x dx, where p and q are polynomials. The degree of p is less than the degree of q, and we've been looking at the special case where q of x can be written as a product of linear factors which have no zeros in common. That is to say, no repeated linear factors. As an example of this sort of thing, I might have a polynomial that the denominator can be factored into these three factors. The idea is I'll write the fraction itself as the sum of three simpler fractions. I'll multiply through by the denominator on the left and get an equation. By putting our special numbers in, we can figure out what the a, the b, and the c are. The resulting three integrals will be easy to do. In the case where the denominator can be written as a product of linear factors, except you have more than one linear factor zero at the same x value, then there is a simple procedure to follow. Instead of having a over x minus 1 plus b over x minus 2, we have to include another term. We have to include b over x minus 1 squared. If it had been x minus 1 to the third power, there would be an additional term involving a constant over x minus 1 cubed, and so on. By putting x equal 1 and x equal 2 into this equation, we can figure out two of the constants. We can figure out what b is and what c is, but I have no third special number to put in to tell me what the a is. Since this equation, though, is supposed to be true no matter what x is, one thought is I'll just pick some particular x and demand that this equation be true. This immediately brings up a thought that won't that depend on which x you pick? We'll check that out in a moment. For convenience, I'll just pick x equals 0. After doing the algebra, it turns out that a has to be negative 2, which turns this integral problem into integrating these three terms, two of which are so familiar with, we'll just write the answer down. The other one, this one, we'll do with a substitution. The first and third integrals are so easy, we'll just write the answer down. The one in the middle, I'll make a substitution. I'll make a u substitution. By now, this sort of thing should be familiar enough with us that no great deal of talking is necessary. As mentioned, though, what if the a that you get depends on which x that you decided to put in? That would make this entire procedure dubious. So let's imagine that I just take some x that I am not going to specify and see what putting it into our equation tells us. If I multiply out all of these equation terms, then equate the coefficients of the x squared piece, the x piece, and the constant coefficient. That'll give me three facts that need to be true in order for this to work out. As mentioned, though, what if the a that you get depends on which x that you decided to put in? That would make this entire procedure dubious. So let's imagine that I just take some x that I am not going to specify and see what putting it into our equation tells us. This is going to give me three equations, each one of which only has a in it. I need to have, if I want consistency, one single a number that works in all three of them, regardless of what the x is. If I solve these three equations separately, I find out that all three of them tell me that a must be -2. So the answer to the question is there's no worries. It doesn't matter which other x I put into that equation that we had. Next, I want to think about what to do if I have a quadratic irreducible factor on the bottom. Because of the whole lower degree divided by higher degree thing, there's only two cases to look at. One is a constant over an irreducible quadratic, and the other is linear. The case of a constant is easy. In the integral 1 over x squared plus 4x plus 5, basically complete the square and then use one of our trig substitutions. In the case where you have a linear function upstairs, we can make use of a trick. The derivative of a quadratic is a linear. So look at the linear function on the top of the fraction and think of modifying its constant coefficient so that the top of the fraction looks like the derivative of the bottom of the fraction. This will split the integral up into two integrals, one of which is easy enough to do with a u substitution, the other one of which is of the type that we just talked about a moment ago. As a parting comment, I'd like to mention that these ideas, in principle, will let you integrate any rational function. As a practice, though, as the functions become more complicated, things become increasingly unpleasant to work with. In this integral, I have not only nice linear factors, but repeated ones as well. I have a irreducible quadratic, and then the square of an irreducible quadratic. If you think about what you're going to have to write down in order to decompose this, it's beginning to get a little bit out of hand. But even so, on a philosophical basis, in principle, you could sit down, figure all of those constants out, and have the integral. This is the last of our integration techniques. Coming up really soon, we're going to make the jump to infinite series, and I'll talk a little bit about how I'm going to proceed with that. In the meantime, I hope everybody has a good day, and I'll talk to you again soon.